Alright, so I'm going to talk a little bit about the technical background of the application. This section and all of the sections following this is going to be aimed towards a more, I guess, technically informed crowd with also rather technical information. So if you're not interested in you're only interested in the functionality of the app, I suggest that you skip this. Okay, so the application is implemented using Django 2.0 with MySQL 5.7 as the database backend. The database calls are largely made using Django query set. This is to prevent SQL injection attacks, and also in general, it's just a cleaner way of doing things. Um, the application is as synchronous as you would expect from a web application, but it might not be tab safe due to a technicality that I made. So essentially, the queries between Django and MySQL, they're represented as query set, as I've mentioned, and for some parts of the application, in particular the search form, for example, uh, the queries are not represented as formatted strings as part of the URL, but rather they are serialized and passed using sessions provided by Django, which essentially allows Django to kind of like serialize a string representation of their internal queries and then pass it through the database and out from the other side. Uh, this, of course, causes the problem of query set consistency. So essentially, your query set is only consistent when when your session object remains the same. Now there are ways around this. For example, coding the template with like a random number, and then call the sessions using that particular random number as a part of an ID process. But I was lazy, didn't implement it, so I cannot guarantee that search results will stay consistent between different tabs. They may not, but they should be consistent between different computers, for example, or different browsers. So yeah, I mean, it's my mistake, but first time web developer, you're bound to make like new mistakes once or twice. I really should have just done everything using like a get response, but I used post, and I was too lazy to fix it later. So, well, maybe it's something to fix in the future. Okay, so since this is a class project, and the class project specified that we have to implement at least 5 advanced database techniques. These are the 5 techniques that we ended up using. Not because we just felt like it, but you will see that most of the time it's because we actually have to. So we used indexing constraint. These two kind of go together. There's also a view. We also use prepare statement and transaction. Now, as I've mentioned, since we implemented the whole thing in Django and Python in general, a lot of these you can do it. Yeah, you don't necessarily have to use straight up raw SQL statements, but to demonstrate that we know what the techniques are and how to do it using raw SQL, for this part, we did a lot of it in raw SQL statement. But like the good practice is, of course, to use like some sort of abstraction, so you don't end up causing security problems and people attacking your website or database with like injections, of course. Okay, so our first 2 advanced database techniques are indexing and constraint, and it's pretty obvious why we decided to use them if you look at the entity relation models that we have. This is made a long time ago when the project was still at its infancy. There might have been some minor changes made to the model by now, but really it's pretty much the same. Like I drew this model, so I kind of knew exactly what's in the database right now. It's very similar to this. Um, And if you see things like this, like for example, account ID, article ID, author IDs, like these are like primary keys, and obviously they will be indexed. So these are the obvious indices. Um, what's not so obvious is the fact that we have also a citation impact field for each article. It's not shown here, and the reason we added the citation impact is for speed, so we don't have to query our our relation that contains all of the citations between the articles every single time we want to find out the number of citations. Um, and if you look at the app, I'll see if I can switch it over there. So if you look at the app, whenever you do a search or just have like a list of articles with some very minor exceptions, all the articles will be listed in a sorted order using their citation impact, right? And similarly, if you go into the article detail and you look at the nodes that are being included inside the citation network graph, those are the top nodes, so to speak, based on their citation impact. So it is very important that the database is able to determine a subset of relevant documents to include based on this metric, the citation impact. And that is the reason why our citation impact is also indexed. And besides the indexing, there is also constraints. In our case, they are largely referential constraints. For example, let's say a user has expressed some interest for an article, and then this will be stored in the interested relation, where on one side is the user ID, which is a primary key. In this case, it will be a foreign key in the interested relation. On the other side would be the article ID, which also is a foreign key inside the interested relation. And whenever there are referential constraints, we utilize cascading delete. So if a user decides, well, let's say an admin decided to delete the user account, which is actually possible if you are an administrator inside our app, but I'm not going to show you that, then the cascading delete will also cause all of the user's interest to be deleted from the interest relation. Alright, so I'm going to show you the SQL definition of the article table in the database that is actually hooked up to the application right now. Here it is. And you can see that yes, indeed, the EID, which is the article ID, is the primary key, and there is a index created for the citation impact field. To show you the foreign key constraint, I'm going to use let's use the citation table. So here, this is a citation table, and you can see that this is a relation that goes from article to article. It's a many-to-many relation, and you can see that indeed it is on one side you have the article ID as a foreign key, and the other side is the another article ID as the foreign key. Okay, so here I'm going to show you the interest model as it is defined inside Django itself. This is a Django model, which is, you can sort of think of it as a Django equivalent of an entity as modeled inside the entity graph, and you can see that it's using, on one side it's using the user ID as a foreign key, the other side is an article, and on delete they will cascade to make sure that if say an interested article was deleted from a database, then this interest entry will also be deleted. And similarly for user, if the user is deleted by an admin, then the interest entry is also deleted. Okay, so before I talk about the next set of advanced techniques that we decided to implement, I think it's a good idea to sort of understand the background, the technical background of why we had to do it. So here is something called a BM25 rank function. Uh, you might be wondering what we're using this for. Well, remember that our title search is produced based on rank score, right? So we want to rank each document. We want to give like a score for each document based on how similar it is to the user's query. Um, and this is the function that we use to actually generate that rank score. I'm not going to go into the detail on why the function works, but if you stare at it long enough, you will realize that this actually satisfies all of the good properties that I mentioned about search. So what is more important for us as database administrators is that the quantities required to actually compute the rank score. So here I mentioned something called Q, which is the process query, and D, which is the process document. By processed, I mean that the query has been tokenized into words, and all the words have been normalized, so the inflected forms gotten rid of and all standardized into a single form. And all of the stop words like is, the, and stuff like that are removed, right? So at that point, I will consider that a processed query or process document. And then you will have to find the actual count of the term inside either Q or D or whatever, right? And W here is of course the standardized form of a word token. Then you have the total number of terms inside D, which is the document length. Then you have something here, the average process document length in the corpus, the total number of documents in the corpus, and the document frequency. So how often this word W appears in documents inside the current collection of documents. You can see that the last three are actually statistics of the corpus. They are not property of a single document, but rather all of the documents together, right? Also, the counted term W in Q, you can imagine that in the entire corpus you might have many different terms, right? From all of these documents. But for each individual document, most of the terms inside the entire corpus are going to have zero count. Right? There are only going to be very few terms for a particular document to have a non-zero count. So if you want to represent the data, at least all of the relevant data for a computation of the rank function inside the database, if somebody tells you that you just store the count of all of the terms you have seen inside the corpus, that would be a terrible idea, because for one thing, you're going to be storing like useless things, zero, most of the time, right? And only very few of them will have one, or anything greater than one. For another thing is like, what if somebody decides to add a new document inside the database? Maybe it has terms that nobody has seen before. Then all of a sudden you will have to enlarge the number of columns inside your article table for all of the rows. That is an extremely expensive operation. So yeah, it's very stupid to do it that way. What is a good way would be to store this as JSON. So inside the JSON file, you will have each of the term followed by the actual count, right? Just for that particular document. You do not have to store any information about terms that do not exist in the document, right? Because you can just assume it to be zero. You only need to record information about terms that actually are inside the document or the query. So you can see what I'm getting at here is that the actual information that you want to store in the database for a document, at least in terms of its title, is a JSON document that contains a non-zero term count, right? Which will give you all of the terms that have non-zero count inside that particular document. And you also want to store the statistic related to the documents, the entire corpus, inside the database somewhere. So I call this process indexing. It's not the same thing as the indexing I was talking about here. No, this indexing process means you process the document inside your database, um, and you generate the term count, you store them as JSON inside each document, then you update the statistic related to your corpus as it goes, right? Okay, so now we're going to talk about the, I guess, further problems that this causes us. Remember that to produce the actual search results, we must compute the rank score for all of the articles in a corpus. And also remember that there are over 1 million articles in the database because we decided to go wide instead of tall. And it happened, and there is nothing I can do to fix that. But now, normally this is actually not a big deal. So imagine that, let's say you're Google, you have all these web pages, you can still return search results very quickly. Why is that? It's because Google was smart enough to come up with distributed computation for the rank scores. So you might have heard about MapReduce, or you might have heard about distributed databases like Google Spanner. These are basically designed to support something like this, right? Because you do not have to compute the rank score for the first document first before you can compute the rank score for the second. You can compute both of them at the same time. So all you need to do is just you produce chunks of your corpus. You send out your chunks to all these different computers, and each of them compute the rank scores for documents contained inside the chunk. And then once they have the rank scores, they send them back. So you will have very high network overhead, but generally very quick computation of the rank scores for the entire corpus. Right? Now, this class requires us to use a traditional database like MySQL on a single node virtual machine. So we do not have this leverage here. We have to do it the old-fashioned way. The unfortunate side effect of this is that it's going to be very slow, especially if you want to do this over 1 million articles, right? So I made a compromise, and my compromise is I limited search to basically just an index subset of the corpus. So essentially, all the articles that are not indexed will be essentially invisible to a search request, that is a title search request. And then I allow the subset to grow dynamically based on user interaction. So what do I mean by that? Well, the thing is, like, the search can still return articles that are not indexed. For example, if you are searching using author, right? You're subsetting the result using author. In that case, the application will assume that an author cannot possibly produce so many articles in his career that that will cause a significant performance problem. So the application will actually try to search the unindexed documents as well. But remember that to actually produce the rank function, we must index the document to produce all these things, right? And to update the statistics. So the solution for that is to dynamically index documents whenever a previously unindexed document is being searched or requires to be indexed. The application will actually go there and update the database to do it, and it will, from that point on, become an indexed document. And as you can imagine, this comes with a plethora of advanced technique requirement, which is why we'd have to use these three: view, prepared, and transaction. Alright, so here are the rules of thumb for document indexing. First one is that a view of the currently indexed document, which of course is a subset of the entire corpus, is, to the surprise of nobody, implemented as a view. Then a document can be added to the index subset, as I've mentioned before, due to the dynamic just-in-time indexing mechanism of the application. However, once it is indexed, it cannot be removed from it, or de-indexed under normal circumstances. It can really only be done manually by someone that has administrator access to the database, like myself, and you have to do it very carefully, otherwise you will cause inconsistency. Alright. Third one is each addition of a document to the index subset causes aggregated statistics like the document frequency of each term, a total number of documents, etc., to be updated. And all of the updates must be carried out very carefully in order to maintain the consistency of the data inside the database. So here I'm going to show you the view of the actual production database. As you can see, there are about 1,045 documents inside the view right now, which means that we have indexed 1,045 documents. Initially, there were only 1,000 indexed document that was seeded. Then the rest of the 45 came from me playing with the app and causing things to be dynamically indexed. So there you go. So apparently it works. I'm just going to generate a DDL so you can see that this is indeed a view of the article table, and it is using the term count field as the condition for the view. So an article is considered to be indexed if its term count field is not null. In reality, term count is a JSON field because, as I have mentioned before, you want to store your term count as a JSON document in order to, for one thing, save space, and another thing to make sure the computation is efficient. And the view is used in the actual application as follows. So notice this function called get bm25 parameters. Essentially, it wants to get the statistic of the actual index subset of the documents. So the statistics are the average document length and the total number of documents, right? The average document length is simply computed as the total title length of all the documents that are indexed divided by the total number of all the documents that are indexed. And of course, you can get that fairly easy from the view. It also returns the actual corpus, which is just the view itself. So there's nothing particularly out of the world here. What may be slightly more interesting, excuse me, is this static method called getTermCount, defined inside the article model. So if you look at this, what it does is it attempts to read the term count of a particular article given the article ID. Now, the read is not a simple get, by the way, because it uses something called select for update. I could probably write this in a raw SQL query as well, but Django provides the functionality, so why not just use it, right? Now, select for update is what is known as a blocking read. What it means is that if the object or entry selected to be read for some reason is undergoing transaction or any sort of a blocking operation, the read will actually fail, or at the very least be queued up. So you will have to wait for the blocking operation to finish. Normally, you will think that why not just read it, right? Like, why do you have to block it? Well, the reason is that even though we're actually like a read operation doesn't actually update the database, we're using the term count to indicate if a particular article is indexed or not. Because if it is indexed, then the term count will not be null, right? However, if it's in fact null, then we must update the article or index the article. So here's a big idea. In order to maintain consistency, we use transaction to index an article document and to update the database. And why do we want to use transaction? Because it is a blocking operation. So transaction essentially maintain consistency by disallowing other operations to come in and update the same row at the same time that you're doing this transaction. Then we use a blocking read when trying to determine if a document needs to be indexed. You don't always have to use blocking read. If you know for sure the document you're reading is already indexed, then there's no reason to use blocking read. You can just read it, right? However, if you're trying to determine if a document needs to be indexed, then you have to use blocking read in case that the document is already being updated. Because then, if you don't use block and read, you will read a null, and then you will try to double update the same document twice. and that of course will cause inconsistency. So here you can see the code I have for actually updating or indexing the document. It's called update term count. You can see that I decided to write a raw MySQL query, even though I probably don't have to, but I want to demonstrate that we in fact understand the point of transaction, and we can actually write raw SQL query to do it. So here transaction is started, and we select a particular update. We'll select a particular row of article for update. Then we actually go there and standardize the title to generate the term count and the title length. Then we go in there and store the term count and the title length. One as a JSON, the other as a simple regular number. And finally, we're going to use a prepare statement to actually update the overall term count document frequencies inside the database. So remember, this is actually a statistic of the corpus, where we simply repeatedly execute this statement. Since this is prepare, you can call a raw SQL statement like this repeatedly by executing it. And the actual statement itself basically just it does a count, right? And then put it in there. So nothing crazy, right? Okay. So you may be wondering, like, what exactly are we doing here? Well, remember that this, despite its name, actually stores document frequencies. I really should change the name of this table. It's confusing. Anyway, so when doing this, you will get essentially two possibilities back. The first one is the term has already been seen before, because it was contained in some other documents. So the entry will have the term itself plus the actual number of documents that has this term, and the count will be 1, right? Because there's exactly one row that has this particular term in it. The other case is when the term is completely new, right? So no other documents has this term so far. In that case, count will be 0 because there are no rows that has this term in it. So this is where magic happens, like where I basically look at the result of this statement and use that to check if the actual term exists or not. If it does, then simply increment it. Increment the current result contained inside the document frequency for that particular term. If it doesn't, then I will have to add it. So I insert the actual term into the document frequency table with the value 1. And then after all of this is done, I finally commit, and at this point transaction is over. So any blocking read will start to actually read afterwards. If there were any other updates coming in, it could happen because maybe some other documents was being indexed, and it also had a particular term, for example, right? So it was being blocked from updating that term frequency, the document frequency for that term. And when that happens, you will now finally be able to update, and you will read the correct document frequency because this is done using transaction, and it should be strongly consistent. Alright, so that's it pretty much for the bulk of the presentation. The question, of course, is what's next, right? If I'm going to work on this any further, I guess the first thing I would do is probably to fix search response, to be using get instead of post. And this will allow me to get rid of the hacky solution of using a session to pass query around, which will probably make things a little bit more, a little bit safer too, in terms of like multiple tabs and stuff like that. Then there's also the idea of implementing distributed computation for rank scores. Then once we have that, we won't need the index subset tag anymore. So we can in fact just use the entire corpus for search. That will obviously produce better search results, but this is not something that can be taken lightly. You will probably require very significant change to the database backend. And we can of course always do with more aggregated statistics for bibliometric analysis. Like we can do some statistics for different institutes, we can produce H-index for different authors, etc. So yeah, that's pretty much it for the presentation for our project. I hope you'll find the application interesting. And as you can see, a lot of effort has gone into it to make the application where it is today. Not to mention all of the logistic issues that we faced throughout the course of this class. So yeah, I hope that our performance is satisfactory, and I hope you enjoyed it. Thank you very much.